So quantum field theory, or QFT, is a very vast subject of physics, and it mostly appears in almost all of the branches of physics except the classical physics. Uh, when you want to delve deeper into the theory, when you are interested in knowing why everything is happening, for example, we study about the reflection of light through a mirror. We know what are the laws of reflection, but when you go deeper and try to understand why the angle of incidence over a mirror, when light is reflected through a mirror, why it is reflected like this, why the angle of incidence is equal to angle of reflection. So these are the very basic things, but when you try to understand why this is happening, why it is reflecting like this, then you have to explain everything through quantum theory, and alone quantum theory is not able sufficient to answer these questions. So we have to go into quantum field theory. So we will not go anything deeper right now in this lecture about the introduction of the subject. We are not going to do the introduction of the subject. We have reserved it for a later point in the course whenever it will be required. So without going further anything about the introduction, let's delve into a few important things, so which are required to carry this course. So to understand quantum field theory, you need some kind of preliminaries like the classical mechanics and quantum mechanics. So I think you must have gone through these subjects like classical mechanics and quantum mechanics. There are some people who are not aware of classical mechanics. They just know that the classical mechanics is all about Newtonian physics, but it's not like that. You need to understand the Lagrangian and Hamiltonian mechanics, then you fully understand the classical mechanics, and that will be helpful in understand in the formalism of quantum mechanics. And then with the knowledge of classical mechanics and quantum mechanics, you will be able to understand quantum field theory. So uh, in this lecture uh, we will be uh, discussing things which will be helpful at our later lectures. So in this lecture we will be discussing a few things which are going to be very crucial in forming the in understanding the preliminary requirements which we are going to require before starting quantum field theory. So let's first start with the Schrödinger's equation, which is minus h square over 2m d2 psi x over dx square. We are writing this Schrödinger's equation sometimes this a is not written, a dot is written here. Okay, Schrödinger's equation. So Schrödinger's equation we are writing, this is the kinetic energy term plus the potential energy. If you are not able to recall the Schrödinger's equation, then you first go and see what is see about Schrödinger's equation. Okay, so this is basically a time independent Schrödinger's equation. Here these are the same psi. Okay, so because there is no time dependence of psi, this psi is the wave function. Psi is the wave function. So now because there is no t term, like if it why this psi is time independent, let's see this. The psi can be written also like this, x comma t, then psi depends both on the position and the time. Okay, but here we have written it only as a function of x, so this is basically a time independent wave function, or you can visualize it like that. The it is expressing a particle at some moment. Okay, so this is the time independent Schrödinger's equation. Now for a free particle, what do you mean by a free particle? A particle which is not influenced by any kind of force. Okay, so Vx, the potential term, okay, will be 0. So let's put Vx 0 minus h square over 2m. It may seem that I have quickly started with this Schrödinger's equation, but as I told you that if you are starting with quantum field theory, you must know about what is a Schrödinger equation. Okay, so Schrödinger equation is the basic of quantum mechanics. So if you are not aware of this Schrödinger's equation, you need to go through quantum mechanics. So it's like the Newton's law for a particle in a microscopic world. So let's put this Vx to be 0. Okay, so this is d2 psi x upon dx square. Okay, plus now this term goes equals e into psi x. Okay, so now we can club these terms to the right hand side or left hand side and write this like this. Okay, so this will become now h square over 2m d2 psi x over dx square plus e psi x equals 0. Okay, now you can see that we can rearrange it. So let's rearrange it. This coefficient we can make it 1. Okay, so unit, so d2 psi x upon dx square multiply by the reciprocal of this, so this will become 2me over h bar square into psi x equals 0. So now we can take this psi as common. Okay, so this will become d2 by dx square plus 2me over h bar square, and this acting on this function equals 0. So this goes sometimes out of my control. Okay, so just excuse me, because sometimes it doesn't respond like I wanted. Okay, now this is working. So now this is a second order homogeneous ordinary differential equation. Okay, so why this is second order? Because you have the second derivative. Now this is homogeneous because in the right hand side we do not have any constant. Okay, so or any other term. So this is equals 0, so this is homogeneous, and this is an ordinary differential equation. Okay, no partial derivative or anything like that. Okay, so to solve this differential equation we have the recipe by putting d over dx, replace this with y. Okay, so if I multiply d by dx or operate twice on any function like fx, so this equals d2 fx over dx square. So operating two times means that if I call this thing as y, then this thing as again y, then fx, then this can be written as y square fx. Okay, so I will be also explaining a few basic things because people from various backgrounds need to study quantum field theory and they are not aware of either quantum mechanics or have better understanding of calculus, or they have forgotten a few things. Okay, so it's better to clear everything and then proceed, because understanding physics is important. Mathematics is just a tool to understand physics, and whenever you are fearful of mathematics, you need to clear your fundamentals. So this is going to our first aim, that everything should be, if anything written on this board, it will be 100% clear, and there should not be any confusion. Okay, we are writing something and we are not able to understand. This is the major problem, because quantum field theory is very intuitive. I told you that we are not going much into we have not gone much into the introduction of this subject, because to go into the introduction will be unnecessary right now, because it can be the case that you even don't know why you need to study quantum field theory. Maybe it's in your course, or I will also invite the people from different backgrounds, like people from different branches of physics who have never met this subject, like they never required to study quantum field theory, like they are from astronomy background and they never required quantum field theory to carry their subject, or people from medical physics or people from engineering background, they do their stuff without quantum field theory. But if they understand quantum field theory, there is a need, because new innovations and new technologies and new developments in physics happens only if we reach a little bit more deeper into the fundamental of the theory, that is physics. So let's come back to this equation. So now we are replacing this by y. So this is the equation. Now we will be replacing this as y square plus 2me over h square and psi x equals 0. Okay, so to solve this equation we have to focus on this polynomial. Like, put this is the recipe actually, this is the procedure to solve this differential equation. Just by solving this polynomial we will find the roots of this polynomial, which is 2me. Solving differential equation is in itself a subject, and to understand quantum mechanics or quantum field theory you actually need to know how to solve differential equation, and sometimes it's become very difficult to uh, figure out the type of differential equation and what are the techniques to solve. Some people refer to some charts or some mathematical physics books. It's even in the engineering physics course or any mathematics, advanced mathematics, calculus. Okay, you can find these kind of equations, how to solve differential equations. So put this thing as 0. Okay, so this implies y square equals minus 2me over h bar square. Okay, so this implies y equals plus minus under root minus 2me over h square, h bar square. So there is a connection between h, which bar, and h, which is Planck's constant. H is the Planck's constant and h bar is h over 2 pi. Okay, this is the, you can say, the angular version of the Planck's constant. So this will be plus minus this minus 1 over square root of minus 1. This is written as iota, the complex unit of number. So this will be I minus iota square root of 2me over h. We have taken out the square term out of the this square root. So these are the two values of y. Okay, so now when you get the solution of y, now the solution for this psi can be written as psi x will be equal to now one thing, a kind of labeling or shortcut, we can write this as k, and the k letter is reserved for this. We will know a little bit later why we are writing it as k. Okay, take it as a constant now. So y is equal to, now y equals plus minus iota, this is iota k. Okay, this whole thing as k. We'll go a little bit more into this later. So psi will be equal to some constant a into e to the power I k x plus b into exponential of minus I k x. So this is a general solution for this kind of equation. If you have the root for this polynomial as given by this, then you can write this term. We have two roots, so for each of the roots we have written this plus ik and this minus ik, and x, because this is a function of x, so obviously x will come. So this is the solution for this ordinary differential equation. Okay, if you are wondering why these exponential terms came here, so you need to go and search about or learn about how to solve this kind of differential equation, why these terms are coming here. And one thing I will like to remind you that e to the power I theta is written as cos theta plus iota sin theta. Okay, so these are the sinusoidal terms, and e to the power I theta can be written like this. Okay, so maybe this will be required somewhere in the simplification of the equations, okay, of the solutions. So now consider a particle, okay, for which we have written the Schrödinger's equation from the beginning. Suppose the particle is moving towards right. So immediately we know that because the particle is moving towards the right, and we have written the Schrödinger's equation as one dimensional Schrödinger equation, because there is only x term, no y or z term. Okay, you can also write the Schrödinger equation in r, theta and phi, okay, in spherical coordinates, but we have written it in Cartesian coordinates. So there is only one coordinate, which is x, like the particle is moving in the x direction. Okay, so this term will obviously become 0. Okay, this term, or basically I should say that this b must be 0, this b must be 0. Okay, so then this psi x will be given as a e to the power I k x, because this term represents the particle going towards left, as this is there is a minus term, and our particle is moving towards right, so this term is 0, so only we are taking only this term. Okay, so now we have written this term. Now again, for simplicity, we can take a as 1. For simplicity, we can take a as 1, or let's just take it as a for now. You can also take it as 1 for simplicity. Now let's go into some inspection. Okay, let's, you know that at some point when you have studied quantum mechanics, so you must have heard that all the observables, okay, like the position and momentum, energy, these things are represented in quantum mechanics in the form of operators. We will discuss a little bit about why we are talking about operators. But just to remind you, you know that in quantum mechanics, the momentum operator, okay, is written as minus I h bar del over del x. This is the partial derivative of x. Okay, so I think you must be aware of the partial derivative. If you are not aware, then you can go and search for partial derivatives. Basically, if you are taking derivative in 3 dimension or 2 dimension, then when you are differentiating with one of the variable, like in x dimension, then you take the another dimension to be constant. So this is basically the momentum along the x, okay, px, for this one dimensional system of particle. So I h bar del over dx. So let's see why this momentum operator is denoted by this minus I h bar del over del x. Okay, answering this question will be very helpful in the further understanding. So let's just apply this px operator on any wave function psi. Okay, I'm taking only time independent functions right now. Okay, so this will be minus I h bar del over del x of the psi x. Okay, let's put this value of psi. Okay, so this will be equal to minus I h bar del over del x, take this thing a e to the power I k x. Okay, so this is a constant, so it will come out. Okay, so minus I h bar a. Now you know that the derivative of exponential is the exponential itself, so it will be e to the power I k x, and then we will differentiate this. Okay, so derivative of this I k x term with respect to x will be I k, these are constant, and derivative of x with respect to x is 1, so this is I k. Now let's multiply this, so it will become I iota into iota gives this iota into iota gives I square, which is minus 1, because this is square root of minus 1 minus 1. This gives you the square root of minus 1 square. This will remove the square root, and this will give you minus 1. So this term and this iota gives you minus 1, and then this is multiplied with this minus sign, and this will give you 1. So h bar and this k, so h bar k, some people call it h cross also, but whatever you call it, then this a term and e to the power I k x. So if I inspect it again, then we find that this is again equal to the psi x. So we can write this as h bar k into psi x. So let's write it very clearly. So now this, okay, this px bar, okay, psi x has given you this h bar k into psi x. So now we can see that when the momentum operator is acting on the wave function of a particle moving in the x positive x direction, expressed by the Schrödinger's wave equation. So Schrödinger's equation is a model which in this era of time being used to express the motion of particle in a microscopic world. Okay, so maybe at some later era Schrödinger's equation may be replaced. Okay, but I think Schrödinger's equation is perfect for this time. So now px acting on psi x gives you this. So we have a direct relation of this as px. Now you know that what is this h bar k. So let's go back and see that what is this. What we have written as k. This is a square root of 2 me over h bar is equal to k. So square root of 2me, I think this is very thick. Square root of 2me over h bar. Okay, this was k. So now if I multiply this thing right in the right hand side, you can get 2me is equal to h bar k. Okay, now what is this square root of 2me? So now you know that the kinetic energy k of a particle, or the total, let's just see the total energy of a particle. Let's consider the whole thing. Total energy of any system, a particle of system of particle or single particle, is given by the sum of kinetic plus potential, because the potential term was 0. This term is 0 from the beginning. So now the total energy is basically equal to the kinetic energy. Okay, and this is the kinetic energy. Basically we have to represent it by T. Okay, because we have represented K for a different term. Okay, so kinetic energy T is equal to is given as half mv square in classical physics, and you know that the momentum of a particle is given by mass into velocity. When you put v as p by m in here, this becomes p over 2m. Now because the kinetic energy term is equal to E, for this situation we can write E as p square over 2m when the potential is 0. Okay, so now we can write that p square is equal to 2me. This implies p is equal to under root 2me. So now we can clearly see that because 2me is equal to h cross k, so we can clearly write it as p. Okay, now we go back and see what we have done. Okay, so you can see that this is equal to p. So this thing can be written as px bar psi x will now become p psi x, and now this thing need to be very important, that momentum operator acting on a function or on a wave function gives you this p. And what is this px? So clearly you can see that this thing, okay, this thing, why this thing is equal to px. So px operator is written as minus I h bar del over del x, because we have seen that minus I h bar del over del x acting on the wave function psi, now we are writing it as psi, gives you basically p into psi x. So that's why this term is written as p. So this is the one of the most important ideas in quantum mechanics. So using this thing, we are going to write one more thing, the commutation bracket of the position and the momentum operators. Okay, so let's write now. So what is the meaning of commutation? So in mathematics you know about different laws of arithmetic, and in algebra about commutation and commutativity and associativity. So these things appear also in quantum theory. Okay, so first we will write the mathematical definition. Simply writing this thing, whenever the two operators are enclosed in a square bracket, this means that this is equal to x bar p bar minus, not bar, this is called an x cap or hat, then p hat and x hat. So in itself this basically is becomes meaningless unless you act this commutation bracket on some operator, but we will apply it on some operator later. Let's just write the value of this operator, how we this operator is, this p operator is represented in quantum mechanics, as we have previously seen that how this momentum operator can be written as this, because acting this this operator on any wave function gives you the same wave function multiplied by h bar and k, and h bar k equals p. Okay, so let's just write it as the position operator will remain the same, and we will write the momentum operator as minus I h bar del over del x, and then this minus again, and then minus I h bar del over del x into this x. Okay, so as I told you that this thing alone is meaningless unless you apply on some operator. Okay, because what is the use if you do not apply it on your operator? So basically in quantum mechanics, if there are two processes, okay, like a process 1 and process 2, it can be anything. So if there are two processes, then you do the first process and then the second process, and you note the effect, or you simply do the second process first and then the first process after that, or let's just call the processes as A and B. There are two processes we are doing with some system. Okay, so you do the process A first, then process B second after it, or you do the first the B process for the first time and then A process after that. Will the effect of this thing will be same? Okay, so obviously you know that this is not same. Okay, you can try it with a dice. Okay, suppose you start with the phase 1, you rotate by 90 degree along the z axis and then along the y axis by 90 degree, or you do the opposite, or rotate first along the y axis with 90 degree and then along the z. Will the effects be same? So the same kind of thing is being done for the operators. Okay, you operate the momentum first, then when let's just apply first it on any wave function, then it will be clear. Okay, so x hat p hat acting on some wave function. Okay, this will be equal to this x bar. Okay, and now we can write the direct this value, minus I h bar del over del x of the psi x minus, now this minus minus will become plus okay. I h bar del over del x, okay. Let's just keep it in the bracket, just only take out the minus sign, okay, and then this x bar, and then we will be writing the psi x, okay. So I think it will be better to remove this bracket for now, okay, and I think this bracket is also not required. So now you can see that if you are applying it on psi, so this thing, this this term will be applied directly to here, but here you can see that this del over del x term will be applied to a product of these two terms, okay. Or simply if I say that if this is acting on psi, then psi will come here, and psi will come here, okay. So p will act first on psi and then x will be multiplied. Here x is directly acting on psi, and then after that p is acting, okay. So there is some kind of difference. There is the same explanation like these processes. You do two of the processes in a different sequence, and we assume that there may be a difference, and if there is some difference, or the output result of the two effects done in a different way, then we can subtract those differences, and we assume that there may be some value associated with it. So if this is subtracted, you get the value of the difference of operating two things in a different manner, okay, in a different sequence. So we are operate, either you operate with momentum first, then position operator, or position first then momentum, and take the difference. So we have taken the difference. Now just apply these things, okay. So this will be equal to minus I h bar, and okay, so this will be just x, and take this as this term as d del psi, or because this is only one dimensional, you can write it as dx, okay, d psi x over dx, okay, plus this I h bar, and then the multiplication of these two terms. So we will write it as, first we will take this x, and then d psi x over dx plus dx over dx, okay. Dx over dx will be 1 into this simply this psi x, okay, simply psi x. Okay, so if I take this I h bar term from this, I would have done it in the starting also, but let's do it now. So if I take I h bar term, then this gives you minus x into d psi over dx plus this x into d psi over dx plus this psi x, okay. So these two terms will go, and we now have I h bar psi x. So now let's see what we have done. We have done this thing, okay. So x p, the two of the operators acting on psi, gave you I h bar psi x. Okay, so now you can see that if I just remove these two things, because these are similar psi, so if I remove this, what we get? This x and p bar, the commutation of this is given as I h bar. So this is one of the most important commutation brackets appearing in quantum mechanics. Okay, yeah, you can also remember this, and the same is valid for the y and z. Okay, so just give a label if you are working in more than one dimension as x, and for let's write all the coordinates simultaneously as x comma px bar will be equal to y comma py bar, no, not bar, cap, z comma pz cap. These three things are equivalent to I h bar. Okay, so we have discussed two important things about the momentum operator. Y momentum operator is minus I h bar d over dx, and how this commutation bracket becomes I h bar using the previous relation of momentum operator. Okay, so in a similar way, you know that energy is also an observable because we measure the energy of a system. Okay, so energy must be associated with some operator in quantum mechanics, and we know that the operator associated with energy is equal to I h bar with a positive sign, del over del t. So now we want to know why the energy term is equal to this. Let's go into this also. Normally these things are not written in books because this is left for the reader. These things are intuitive, but sometimes when you are reading, trying to develop theory from books, a few things are missed, and you understand quantum mechanics in a way which you perceive from the book. In the book, what the author is trying to explain may be different than what you have understood. So now we want to see why this energy operator is written like this. Okay, so to understand this, we can simply apply this operator to psi, and you have to guess what I am doing wrong. Okay, then we will be doing the right thing. First we will be do something wrong here. Okay, so let's apply this E to the psi. Okay, so now I'm applying this E to psi, and going through this will take you to a very crucial concept in quantum mechanics. This is one of the most crucial concepts you need to know when you are studying quantum mechanics or quantum field theory. So if I apply this energy operator to a wave function, then this will be equal to I h bar del over del t on psi x. So now if I write this thing as I h bar del over del t of a into e to the power I k x. Okay, so if I write psi x like this, then this will become I h bar. This a term will be out, and then the exponential term e to the power I k x. Okay, not here, this will bracket, and then the derivative of this term. So this will give you the constant I k, and now this x, because we are differentiating with respect to, because this is now two things are involved. Okay, this is del, not d over dt. Okay, for one dimension, you may think like that, for one dimension why I need to write this as del over del t. If I write this as d by dt, okay, d by dt, okay, just following the last case. Okay, so now this will become, this I k term will be, and then dx over dt. Okay, and you may think that this dx over dt is the velocity term, so you will write it as velocity. Okay, so if this is velocity, then I can write this as I h bar, and this term will be written as psi x. Okay, also this I into I will give you -1. Okay, so better I think I should remove this iota term. Okay, and instead I should write minus h bar and this k term. Okay, and then this dx over dt is velocity, which is given by momentum over mass. Okay, now you know that this momentum, we have already written this, that h cross k is equal to the momentum. Okay, the momentum. So I will write this p as equal to this h cross k, we can write as either as p. Okay, so maybe I can write this as p. Okay, let's just write it as minus p, and this p square upon m and psi x. So now you can see that when this term, okay, when this e to the power this I h bar del over del t acted on this psi, okay, we got this thing. Okay, let's just check it once again. I think there may be some mistake in it. So I h bar we differentiated with time, so this is a term. Okay, okay, this is okay, so this is a, and this term, then I k, then dx over dt, and this is equal to v. I and I gives you -1, then h bar k, this gives you p, and this p and p multiplied p square. We have written v as v is equal to momentum upon time, so we have written this. So now you can see that when we acted I h bar del over del t or d by dt, we have replaced del over del t by d by, because of one dimension. Okay, people go in understanding the things, how people go understanding the things in a wrong way. Basically we are trying to figure this here, and as I told you, we will, why this is not working, and now this is fine. As I told you, we will we will encounter a very crucial concept in quantum mechanics. So this del over del t term, okay, when this was acted on psi x, this gave you minus p square upon m psi x. Did it give you energy term? Energy is given as for the kinetic energy p square over 2m, but now you can see that this is not giving you the right thing, and even this is giving you a negative thing, negative sign. So obviously this is not working. So why this is not working like that? Because you can see why we are writing this as del over del t, not d over dt. Okay, so this wave function is time independent wave function, and energy is given by the time evolution. Okay, the rate of change of the wave function with respect to time. And so basically I want to say you that if I differentiate psi, okay, with respect to time, okay, so del psi over del t, and you want to write it like this: del psi over del x into del x by del t, and then this thing as the velocity, then basically we are on the wrong track. In quantum mechanics, the position or the trajectory of a particle cannot be defined, because you know from the uncertainty principle del x into del p must be greater than this h bar. So I think I missed 2 over here. So you know that from uncertainty principle we know that we cannot measure momentum and position simultaneously, and because we cannot measure, it doesn't mean about measurement. It's not about the measurement or the instruments are not perfect. A particle in the microscopic world by itself, by the nature, the position of the particle is not certain. The particle can be anywhere. Okay. In classical physics, a particle is following a trajectory. There is a well-defined trajectory of the particle given by the function. Okay, I can give a position vector like in the space. Okay, the position of the particle is given by some this r vector. Okay, is a function of x comma y comma z, and for a one dimensional particle which is moving in the x direction, the position is simply given by just x. Okay, this is given by just x. How the x is changing? So x is basically a function of time. So in that case, in the case of in classical physics, we calculate dx by dt, and the rate of change of position of particle is denoted as velocity. And when we multiply mass of the particle to both hand sides, it becomes the momentum of the particle. But that is not the case in quantum mechanics. The particle is here, and suddenly the particle disappears and appears here. The particle can be present at two places, more than one places at the same time. So there is no specific trajectory for the particle. So in quantum mechanics, okay, you do not have things like dx over dt, okay, or del x over dt if you are taking x as some position function. So basically dx over dt terms is completely absent in quantum mechanics, because there is no fixed trajectory for the particle. So this term the way we have differentiated, we have started from here. Okay, so I told you to guess there is something wrong. Okay, that something wrong thing we have taken is that this psi itself, we are differentiating psi which is time independent, and something which is time independent, when you differentiate it with t, okay, this term will this derivative will simply become 0. Okay, so in quantum theory, time and position position and time are two different variables. Okay, there is nothing like the position of the particle depends on time. Okay, there is nothing like this. Okay, x and t are basically two different observables. And why they are observable? Because the position of particle can be anywhere in the space and there is no fixed trajectory. So we want to find the position of the particle at any given position or at any given time. Okay, so the we need to calculate the probability whether the particle is present over this space, in this space, in this three-dimensional space. What is the chances of getting that particle? And to get the probability of that particle, we basically define a function which we call the wave function, because basically the probability of getting a particle in the volume of a space is changing, because uh, it's not like that the probability is always constant. The probability of finding the particle may change, so we define that thing with a wave function. And because this is changing over the space and with respect to time, as the time evolves, the probability of the particle may change at a given point. Suppose at this point the probability is p1, then after some time the probability may be p2. So this psi is a function of both position and time, because we want to measure the position of the particle at a given time. Okay, so uh, so basically x, the position is taken as the operator. Time is the variable. Actually the variable time is not any operator here. Okay, so but when we will take the commutation bracket of energy, we will take it with time. Okay, so there sometimes time look like an operator. So energy and time. Okay, uh, now let's go back and see. I think one thing we are missing, that how this is equal to E. Let's go back to this and let's remove this for now. Okay, so now what gone wrong in writing the psi? So we now have to write psi x comma t instead of just psi x, which is time independent wave function, because energy is all about the evolution in time. Okay, so and momentum is written as the derivative of the wave function, because let's just write this as, so we can split in two variables like this, psi as a function of x, and the exponential term e to the power minus I e t. Okay, E is the energy of the particle. So why we write psi like this? Because we know that the position and time are two different position is different from time. You do not take a derivative of x with t. So we have separated these two things. This is the first inference. Now why this exponential term? Okay, because we have also used the exponential term previously for the momentum. So you know that for a wave, to describe a wave, you need some trigonometric functions like sine theta and cos theta. Okay, so you know that the functions like sine theta or cos theta, the graph of sine theta and cos theta is like this, and a linear combination may also be a wave like this, a linear combination of sine and cos, but it is somewhat different from just a linear combination. You write exponentially to the power I theta as cos theta plus iota sine theta. So it's a complex, basically a complex function because iota is involved. So at this point basically it will be not too intuitive to understand why we have taken this iota term, but once we will calculate the probability density, then it will be clear why this iota was introduced. Okay, so let's first differentiate it with let's add the energy operator both sides. Okay, so you know that energy operator is I h bar del over del t, and if I apply here phi x into e to the power minus I e t, okay, then this will be equal to I h bar, this because this is x, and this depends on this phi depends on x, and x doesn't depend on t. X is not a function because x in quantum theory there is no fixed trajectory. Okay, so we will simply take out this term because we have already written here this thing, just to keep you remind you. I've written somewhere, yeah, this thing. You cannot write like this in quantum theory. You cannot write like this. Okay, there is no dx over dt term. So if I want to differentiate this, this will be just treated like as a constant. So take phi x out of the way and then differentiate del over del t e to the power minus et. Okay, simply. So it will be I h bar phi x minus et term minus I, not et. Okay. Okay, and this dt over dt will go. Okay, so if I multiply this I and I give you minus 1, and this minus will be cancelled. So h bar, this is giving you h bar into this e and then phi x. So I think you need one more term. Okay, so let's divide this term by h bar. Okay, now we can go logically because we are getting this e term, so better you know that if we divide it by h bar, and it must be like that because the term which is appearing in the exponent must be a dimensionless quantity, dimensionless. And if you see clearly, I e t over h bar, the units of the numerator is joules into second, and this h bar, the Planck's constant, the unit is joule second. So joule second cancel out and you get a unitless quantity, and the same thing is for the e to the power I k x. Okay, so this term, I think this is divided by h bar, and then this will be divided by h bar. So this h bar will go, and this h bar will not be here. So simply this is e into phi, and e into phi x, and this one thing we missed, that is when you differentiate the exponential function, there is an exponential term which is I think I should write it very clearly here. Okay, so when I differentiated it, it should be e to the power minus I et over h bar, and then the derivative of this, so this is minus I e over h bar. Now this h bar will cancel with this, and this will give you e phi x e to the power minus I et over h bar. So now I think you will not be puzzled when someone writes a wave function like this. Why there is a h bar in the denominator? Why this I et is written? Okay, so you can see that if this operator is acting on the wave function, okay, which is consisting of both the position function and the energy term, okay, exponential term for the time, then when this acted, it gave you the energy term E, and the same this phi x, this gives you this psi x comma t. Okay, so now you understand why this term I h bar del over del t, this is t, is corresponds to the energy operator in quantum mechanics. So we will continue with from here in our next lecture. Now I want to make you clear that in the starting you will find that we are actually deviating from, it looks like to you that we if I am deviating from quantum field theory, but I will keep you reminding that these are the preliminaries which is very important in the understanding and building the theory further, because writing anything without understanding it with heart will not take you further in the development of quantum field theory. Okay, the theory is very vast and used in different branches of physics. So I encourage you to go through the preliminaries first, and then we will be delving into the field of quantum field theory. So thank you.